In 2015, Google's engineering team ran a projection that terrified them. If every Android user utilized voice search for just 3 minutes a day, Google would need to double its entire global data center footprint just to handle the processing load. Buying more off-the-shelf central processing units was financially and mathematically impossible. The sheer volume of hardware required would bankrupt the project before it began. The problem was the specific type of math required: deep learning, specifically convolutional neural networks, or CNNs. Algorithms designed to process pixel data for image and voice recognition rely almost entirely on billions of low-precision matrix multiplications. To survive this incoming wave of compute demand, Google engineer Norman Jope was handed a mandate: execute a secret crash project to design an application-specific integrated circuit, or ASIC, from the ground up in just 15 months. An ASIC is a microchip designed for a single, highly specific use, rather than general-purpose computing. The physical solution they built didn't require entirely new server farms. The chips were mounted inside custom heat-sink assemblies, engineered to slide directly into existing hard drive slots within Google's established data center racks. Google could no longer rely on the broader semiconductor industry's roadmap. To scale artificial intelligence, they had to stop using general-purpose hardware for neural network inference. This animated diagram illustrates standard CPU architecture, defined by the von Neumann bottleneck. To perform a calculation, the processor must fetch an instruction from memory, move it to a register, execute the math in the arithmetic logic unit, the digital circuit that performs operations, and then write the result back to memory. This continuous back-and-forth fetch-execute-store cycle takes a toll. Moving the data across the chip consumes significantly more time and electrical energy than the actual mathematical computation itself. Graphics processing units offer massive parallel processing capabilities, but they still carry architectural baggage. GPUs dedicate significant silicon to complex features like texture mapping and rasterization, operations essential for rendering video games, but unnecessary for multiplying neural network matrices. By stripping away that overhead, the resulting tensor processing unit achieved massive gains. According to a 2017 paper presented by Jope, the first-generation TPU delivered 15 to 30 times higher performance and 30 to 80 times higher performance per watt than contemporary CPUs and GPUs. This efficiency leap was accomplished by aligning the physical layout of the silicon directly with the continuous mathematical flow of matrix multiplication. Breaking the memory bottleneck required a structural departure. Google had to stop treating memory and computation as isolated steps and instead merge them into a single continuous physical flow. The TPU's matrix multiply unit is a massive grid of 8-bit multipliers. In this systolic array, data flows like a pumping heart, entering the top and left edges. Results pass directly to neighboring multipliers every clock cycle, cascading and accumulating sequentially. Unlike the von Neumann cycle, intermediate results are never written back to outside memory. The TPU performs thousands of operations for every memory access. Manufactured on a 28-nanometer process at 700 MHz, the TPU V1 consumed just 40 watts while yielding 23 trillion operations per second. However, the first-generation chip had a strict limitation. It was built exclusively for 8-bit integer math. This made it highly efficient for inference, running existing models to generate answers, but useless for the heavy lifting of training new neural networks. The systolic array solved inference efficiency. To conquer the training phase, Google engineers had to alter the way computers represent numbers. Training a neural network requires calculating tiny gradient updates during backpropagation to adjust network weights. This extreme precision requires floating-point mathematics. Standard float 16 has 1 sign bit, 5 exponent bits, and 10 fraction bits. 5 exponent bits lack the dynamic range for deep learning, ruining training. Google's TPU v2 introduced bfloat 16, trading fraction precision for extended dynamic range. Matching the 8 exponent bits of a 32-bit float, bfloat 16 achieves a massive dynamic range from 10 to the -6th to 10 to the 6th, while cutting the memory footprint in half. This specific optimization triggered a lengthy legal battle. In 2019, Singular Computing filed a patent infringement lawsuit against Google over the hardware design. Singular claimed this non-standard floating point format was their patented invention. The litigation dragged on until Google agreed to an undisclosed settlement in early 2024. The TPU v2 could now handle both training and inference. But this massive processing capability exposed a new physical bottleneck: feeding data into the chip. Engineers call this the memory wall. The systolic array calculates matrices at blinding speeds, but its throughput is entirely dictated by data piping speed. This chart tracks memory bandwidth across TPU generations. V1 used off-chip DDR3 memory at 34 gigabytes per second. Partnering with Broadcom, Google shifted to high-bandwidth memory for V2 and V3, stacking it directly adjacent to the die. Bandwidth spiked to 900 gigabytes per second. Google also scaled outward, arranging TPUs into massive supercomputing clusters called pods. This culminates in the 2025 TPU V7 Ironwood generation. Equipped with 192 gigabytes of high-bandwidth memory, its bandwidth skyrockets to 7.37 terabytes per second. A maximum-scale Ironwood cluster connects up to 9,216 chips via optically reconfigurable networks. Together, they act as a single training engine capable of 4.6 quadrillion floating-point operations per second. The TPU evolved from a single chip into a warehouse-scale supercomputer. Delivering AI performance is now a complex thermal engineering problem beyond pure silicon design. While Google built 170-watt server rack behemoths for the cloud, they also pursued the opposite end of the compute spectrum: edge computing, which processes data locally on the device itself rather than relying on a centralized server. They introduced the Edge TPU under the Coral brand. It is a miniaturized, purpose-built ASIC capable of 4 trillion operations per second, while drawing only 2 watts of electrical power. To achieve this power draw, the architecture accepts strict limitations. It relies entirely on 8-bit math, meaning models require quantization-aware training, a technique that simulates lower precision math during the training phase so the model remains accurate when compressed. The Edge TPU also only accelerates forward pass inference operations. Google integrated this architecture directly into its Pixel smartphones, first as the Pixel Neural Core, and later baking it into the custom Google Tensor system-on-chip. For the user, the practical benefit is machine learning performance that allows for features like real-time computational photography while simultaneously reducing instantaneous power consumption to preserve battery life. The fundamental mathematical efficiency of the systolic array scales perfectly in both directions, whether it is training a trillion-parameter model in a liquid-cooled pod or processing an image in a user's pocket. By matching the physical layout of the silicon directly to the mathematical shape of tensors, Google secured an immediate 7-year technological leap over the rest of the industry. General-purpose central processing units no longer receive the consistent performance gains from Moore's law necessary to sustain this level of growth. The future of high-performance computing now belongs to domain-specific architectures. The path forward demands custom hardware built not to do everything adequately, but to execute one complex mathematical task perfectly.